This is SpaceTime, Series 20, Episode 32. Coming up on SpaceTime, the number of monster black holes in the universe has just doubled. Astronomers move a step closer to solving the mystery of pulsars. And the first results from the Breakthrough Listen initiative looking for intelligent life beyond Earth. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
The number of monster black holes thought to exist across the universe has just doubled. The findings are based on the discovery of two supermassive black holes in the ultra-compact dwarf remnants of a pair of shredded galaxies. The study, reported in the Astrophysical Journal, supports the idea that ultra-compact dwarf galaxies are in reality the leftover remains of much larger galaxies that have been cannibalized by other galaxies. Black holes are among the strangest objects in the universe. Incredible gravity wells that suck in and destroy anything that gets too close. Stellar mass black holes are created out of the collapse of the biggest stars, while supermassive black holes, millions to billions of times more massive than the Sun, are thought to exist at the centers of most, if not all, galaxies. Galaxies grow by merging or cannibalizing each other. For example, right now our own galaxy, the Milky Way, is cannibalizing a much smaller satellite galaxy called the Sagittarius dwarf. At the same time, it's also stripping stars from two other dwarf galaxies, the Large and Small Magellanic Clouds. And in about 3.5 billion years from now, the Milky Way itself will be cannibalized as we merge into the larger Andromeda galaxy M31. As the gas and stars in the progenitor galaxies combine to form a new bigger galaxy, it was thought their central supermassive black holes merge. However, 3 years ago, astronomers from the University of Utah discovered an ultra-compact dwarf galaxy containing a supermassive black hole. At the time, this was the smallest known galaxy to harbour such a giant black hole. The detection of a surviving supermassive black hole in this galaxy remnant suggested that only the galaxy's outer layers of stars and gas were stripped away after colliding with the larger galaxy, and material close to the galactic centre, including the black hole, survived the event. Now the same team of astronomers have found two more ultra-compact dwarf galaxies containing supermassive black holes. Together, these three samples suggest that black holes lurk at the centre of most of these objects, potentially doubling the number of supermassive black holes in the known universe. The black holes make up a high percentage of the compact galaxy's total mass. That supports the theory that the dwarfs are in fact remnants of larger galaxies ripped apart by even bigger ones. The study's lead author, Chris Arndt from the University of Utah, admits scientists still don't fully understand how galaxies form and evolve over time, and so these objects can tell astronomers more about how galaxies actually do merge and collide. The authors measured two ultra-compact dwarf galaxies, named VUCD3 and M59CO. Both are orbiting massive galaxies in the Virgo cluster, which lies far beyond the spiral arms of our own Milky Way. The authors detected a supermassive black hole in each galaxy. VUCD3's black hole has a mass of about 4.4 million times that of our Sun, making up about 13% of the galaxy's total mass. And the black hole discovered in M59CO is even bigger, with some 5.8 million solar masses, making up some 18% of the galaxy's total mass. Now, by comparison, Sagittarius A star, that's the supermassive black hole at the centre of the Milky Way, has about 4 million solar masses. And that means it makes up less than 0.1% of our galaxy's total mass. To calculate the ultra-compact dwarf galaxy's mass, the astronomers measured the movement of stars using the Gemini North Telescope located on Mauna Kea in Hawaii. The Gemini telescope is equipped with adaptive optics, which uses lasers to measure distortions in light caused by Earth's atmosphere. For astronomers, trying to look at stars through Earth's atmosphere is a bit like looking at the sky through all the water from the bottom of the pool. The distortions are caused by different atmospheric layers at different temperatures. After reading the distortions in the atmosphere detected by the lasers, the adaptive optics' powerful computers are then used to modify the telescope's flexible mirror hundreds of times a second in order to counteract the atmospheric distortion effect. The authors applied the same technique to their ultra-compact dwarf galaxies, which are so small that the corrections are necessary to measure the motions inside the galaxy, thereby bringing the once blurry galaxies into sharp focus. The research team also analysed images from the Hubble Space Telescope to measure the distribution of stars in each galaxy, and then create a computer model to fit their observations. They found that the motion of the stars at the centre of the galaxies moved much faster than those on the outside, and that's a classic signature for a black hole. Astronomers first discovered ultra-compact dwarf galaxies back in the 1990s. These objects are made up of hundreds of millions of stars, all packed densely together in an object just 100 light-years across, just 1,000th the diameter of the Milky Way. When scientists studied the centres of these galaxies, they were surprised to find that ultra-compact dwarf galaxies had far more mass than their stars alone could account for. And that indicates the likely presence of some extremely massive compact central object, and that description exactly describes a black hole. An alternative hypothesis would have involved ultra-compact dwarf galaxies being unusually large star clusters. Star clusters are dense balls containing hundreds of thousands of stars which were all born at the same time out of the same molecular gas and dust clouds. The problem is, even the very largest known star cluster in the Milky Way only contains about 3 million stars, while ultra-compact dwarf galaxies are between 10 and 100 times bigger. And that raises the question of whether or not they're formed in the same way as star clusters, or whether they're formed by some completely different process. The discovery of central supermassive black holes in these objects shows that they are indeed very different. These new findings suggest that ultra-compact dwarf galaxies were indeed once far larger galaxies, containing billions of stars, just like the Milky Way. However, over time they were cannibalized by other galaxies, leaving only the core remaining, like scraps on the giant cosmic banqueting table. The findings will change the way astronomers piece together how galaxies form and evolve over time, with ultra-compact dwarf galaxies providing a longer timeline to enable astronomers to better see what's happened in the past. This is SpaceTime. I'm Stuart Gary. Astronomers are a step closer to uncovering the mystery of how rapidly spinning neutron stars called pulsars generate their powerful energy beams. The findings, reported in the Astrophysical Journal, indicates the beams are far more complex than previously thought. Neutron stars are the stellar corpses of stars far more massive than the Sun, which have been destroyed in core collapse supernova explosions. These powerful cataclysmic blasts, marking the death of some of the universe's biggest stars, are bright enough to outshine entire galaxies. The neutron star is the highly magnetized, extremely dense core remnant of the star that exploded. It contains more mass than the Sun, but squeezed into an object just 20 kilometers across, and that makes neutron stars as dense as the nucleus of an atom. Neutron stars also spin rapidly, emitting powerful beams of energy into space as they rotate. These rapidly rotating beams look like celestial lighthouse beacons, pulsing in the night. If Earth just happens to lie along the line of sight of one of these beams, radio telescopes can detect the neutron star as a pulsing source known as a pulsar. Thousands of pulsars have been seen since their first discovery back in the late 1960s, but questions still remain as to why these stars emit radio beams in the first place, and also what type of emission model best describes the radio waves or light that's being seen. The new research suggests the answer could lie in a sort of drifting carousel found in a special class of pulsars. The study's lead author, Sam McSweeney from Curtin University and the International Centre for Radio Astronomy Research, says the new findings have uncovered some extremely complex signals. The classical pulsar model pictures the emission shooting out from the magnetic poles of the pulsar as a light cone. But the signals the authors observed indicates a far more complex structure lies behind the emission, probably coming from several different emission regions, not just one. McSweeney says the drifting carousel model manages to explain this complexity much better. He describes the emission as coming from patches of charged particles, probably arranged in a rotating ring around magnetic field lines. In other words, the carousel. As each patch releases radiation, the rotation generates a small drift in the observed signal of each of these sub-pulsars that McSweeney and colleagues were able to detect using the Murchison Wide Field Array Radio Telescope in the Western Australian outback. Occasionally, the authors found that this sub-pulse carousel gets faster and then slower again. And that could be providing a new window into the plasma physics underlying the pulsar emission. One possibility is that surface temperature is responsible for the carousel changing rotational speed, with localized hotspots on the pulsar surface causing it to speed up. McSweeney now wants to observe individual pulses from these drifting pulsars across a range of different radio frequencies at far lower frequencies than ever before. Looking at the same pulsar with different telescopes simultaneously will allow him to trace the emission at different heights above the pulsar surface. He says he now plans to combine data from the Murchison Wide Field Array with that from the Giant Meter Wave Telescope in India and the CSIRO's 64-metre Parkes Radio Telescope in New South Wales.
You have hit the salient points quite nicely. So the devil is in the details, and what we're trying to do is really understand how the shape of the beam looks the way it does. There are any number of models that go back to the 70s of describing the basic idea, giving us the basic picture, but we still don't have a good handle on the details. There's not just one idea. There are, of course, multiple ideas floating around, but one of the more common ones is pretty much what you described, where you have charged particles in the environment of the pulsar, and that cloud of charged particles around the pulsar we call the magnetosphere, and they're being accelerated out relativistically from the surface. And as they go out, they follow the magnetic field lines, and the curvature of the magnetic field lines provides acceleration, which causes the charged particles to radiate. And you can sit down and you can work out just how much energy these particles would have to have in order to be able to send out a radio beam, that is a beam in the radio part of the spectrum. So far so good. We have that basic idea. But the trouble is that the beam structure, obviously, when you look at some of the pulsar signals, it must have a lot more detailed structure than just a solid cone of light coming out towards you. So one of the early ideas, perhaps going back to, well, even going back to the 70s, really, is that the structure of the cone is not a solid cone, if you can imagine a solid cone of light coming kind of uniform across the cross-section of that cone. It's not like that. It was evident pretty early on that you would have to have, for example, you might have a hollow cone structure. So in that case, you've got light kind of coming along the surface of a cone towards you, and the middle would be devoid of radiation. But because the pulsar is spinning, what you see is just a cross-section of that cross-section, so to speak. So you'd only kind of cut into the cone at an early part of the pulsar spin, and then you cut out of the cone later on. So this kind of tallies up nicely with what we see in many pulsar signals, which is a double-peaked structure to their what we call a pulse profile. But even that can't explain everything, because some pulsars don't just have two peaks. Many have one, many have two, but some have more. So there's like 3, 5, even up to 13 different peaks in their profile.
When you look at the light curve of a pulsar, you can picture the two peaks depending on the angle you're looking at it from. But when you start to talk about multiple peaks, 13, wow, that's head-scratching.
Yeah, so you have any number of ideas trying to explain that. For example, you can have nested cones. So you would have an outer kind of cone structure of light, and then another one a little bit closer in, and perhaps more closer in. Generally speaking, they try to classify pulsars in terms of conal emission, which is this ring of emission coming out, and also core emission. So you might have something in the middle. So that would explain 3 peaks, for instance, because if your line of sight just happened to cut right across the middle of that cone, you might pick up the 2 conal components on the outside of your profile, and then in the middle you would have a core component. So 3 can be explained, and then any kind of odd number after that can be explained with nested cones, but it gets awfully complicated, and no one really has an idea of what could cause that entire structure to be the way it is.
What does this tell us about the way the pulse in a pulsar is generated in the first place?
So if you go back again to the 70s and have a look at some of those early models, one of the really kind of long-standing ideas is that you have pockets of charged particles which kind of are accelerated suddenly and all at once. And these pockets of charged particles kind of are localized in a particular place or near the pulsar's surface. And the idea is that these pockets, which are all the time generating relativistic particles, are moving around the magnetic axis as they go. And the idea of what could generate a ring of such particles would be that you have multiple discrete pockets, and those particles are being influenced by what we call E cross B drift. So E stands for electric field and B stands for magnetic field. And the combination of the electric and the magnetic fields provides a torque that carries that pocket of charged particles around the magnetic axis. So they have a kind of a natural
twist,
circular motion, as around that axis. And so that would kind of give you a conal structure. So that's one idea. But one of the troubles with that idea is that it predicts 2 things. First of all, that the cone has to be exactly circular. And second of all, that the rate at which that pocket of charged particles moves around the magnetic axis is constant. But the gist of what I'm showing for this particular pulsar that I've been looking at is that you can't have constant motion to explain its signal.
Tell me a little bit about the observations you've made now. Let's unpack that a little bit.
The pulsar's name, well, it doesn't have a name. It has a designation.
Sure.
So it's called PSR for pulsar, J0034-0721. And those numbers are actually just its coordinates in the sky, and that's their naming convention. They just pick the coordinates of where it is, and that becomes its name.
It's very romantic.
It's so romantic. But you get to know, we call them phone numbers. What's that pulsar's phone number?
Tell me about the observations you made of this particular pulsar.
We chose this particular pulsar because we knew it was a special type of pulsar called a drifter, which is to say that when you look at each individual pulse, you can actually see the structure which comes from, we suppose, these charged particles moving around the magnetic axis.
These charged particles themselves, do we know where this cloud of charged particles originates from? Is it from the surface? Is it just debris from the progenitor star? Do we know?
There's at least two ideas that I can detail for you of where these charged particles come from, and I think both of them are quite interesting and exotic, and it's definitely not nailed down which of these possibilities is true. One idea is what you said, which is that they might come from the surface of the pulsar, and it's not that they just kind of evaporate off the pulsar, but the really strong electric and magnetic fields surrounding the pulsar actually would pull either positrons or electrons or even perhaps ions off the surface and accelerate them. So that's one possibility. Another possibility, which I think is more favored, but perhaps don't quote me on that, is that the particles are actually generated from incoming photons, which spontaneously decay into an electron-positron pair. And then each of those are pulled immediately and accelerated immediately by the strong fields. So you have this kind of soup of positrons and electrons that are constantly being created and annihilated, but obviously more created than annihilated in order to give you the charged particles that we know must be there. Yeah, so that's the other idea, that they're just spontaneously being created.
Would there be any characteristic about the pulsar over time that would point to one hypothesis as opposed to the other hypothesis?
I think to get at which of those scenarios is correct, really what we're trying to do is nail down all of these little details about the radio emission mechanism. I think that's our best clue. And so that's exactly a kind of what I'm getting at with my work, but not as directly as all that. If we can figure out exactly where the emission takes place in the magnetosphere, then we can say something about the conditions of that pocket of magnetosphere that would generate that emission. It's really trying to map out where the emission takes place. It's one thing to say, okay, well, we can see the beam that looks like this, so the beam must have this structure. But even knowing the shape of the beam doesn't actually tell you immediately where above the pulsar surface the emission happens. And until we can even say that, we won't be able to say what the magnetosphere is doing at those locations. But I think once we figure that out, then yeah, it does. It does. It's a 50-year-old mystery, and it's still going on. But it's exciting because there's so much observational data out there that it's really tempting to think that there should be an answer by now, but there frankly isn't. So we're missing something important, perhaps.
That's Samuel McSweeney from Curtin University. And this is SpaceTime. I'm Stuart Gary. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. The Breakthrough Listen Initiative, which is searching the skies for signs of extraterrestrial intelligence, claims it's found 11 events regarded as being sufficiently significant to be worthy of further investigation. The findings, reported on the pre-press physics website archive.org, were part of the petabytes of data collected during the first year of observations using the National Science Foundation's Greenbank Radio Telescope in West Virginia. Breakthrough Listen scientists say it's unlikely that any of these signals originate from artificial extraterrestrial sources, in other words, aliens. But even so, they were above the pipeline threshold for what's considered to be a significant event. The findings represent part of an analysis of 692 stars, comprising all spectral types, taken with the L-band receiver at Greenbank, which covers frequencies from 1.1 to 1.9 gigahertz. Scientists with the University of California, Berkeley's SETI, Search for Extraterrestrial Intelligence Research Center, designed and built the analysis pipeline to scan through billions of radio channels in search for unique signals that might indicate the presence of technology developed by civilizations outside our solar system. As well as Greenbank, Breakthrough Listen, which is funded by Russian physicist Yuri Milner, also uses the Lick Observatory's automated planet finder at Mount Hamilton in California and the Parkes Radio Telescope in the central west of New South Wales. The basics for searching for signals of extraterrestrial technology are really quite simple. Artificial signatures can be distinguished from natural processes through features like narrow bandwidth, irregular spectral behavior, pulsing or modulation patterns, and by broadband signals with unusual characteristics. The problem is human technology emits signals known as radio frequency interference, similar to the ones being searched for. This means that algorithms need to be designed to ensure the signals are coming from fixed points in space relative to background stars or other targets being observed, and not from local human sources, such as Earth-orbiting satellites, radio stations, or even microwave ovens. The Berkeley SETI Research Center Breakthrough Listen science team examined data on the 692 stars from the primary target list from the Greenbank telescope, consisting of 3 5-minute observations per star, interspersed with 5-minute observations of a set of secondary targets. By performing an analysis of threshold frequency channels, as well as a Doppler drift search, the pipeline produced millions of hits for the sample as a whole, of which the vast majority are almost certainly radio frequency interference from human technology. However, there were these 11 events which rose above the pipeline threshold for significance. Further detailed observations indicate that it's unlikely that any of these signals originate from artificial extraterrestrial intelligence. In other words, ETs not phoning home. For each star sample, the team searched through the entire database of events, looking for radio channels where events occurred only at one or a small handful of positions in the sky. While these stars have unique radio fingerprints, this is by no means convincing evidence that they host planets inhabited by extraterrestrial civilizations. However, the search for signals that are localized on the sky and appear unusual in some way provides an excellent way to select promising targets for follow-up observations. I'm Stuart Gary. This is SpaceTime. Two new crew members have arrived aboard the International Space Station. The Expedition 5152 crew blasted off from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan aboard their Soyuz MS-04 capsule on a 6-hour fast rendezvous flight to the orbiting outpost. The launch also celebrated the 56th anniversary of the flight of Yuri Gagarin to become the first human to fly in space, also launching from the Baikonur Cosmodrome. The Soyuz FG launch vehicle blasted off into clear skies using its single liquid oxygen and kerosene-fueled core stage RD-108 engine and 4 RD-107A strap-on boosters.
Vehicle to internal power.
There's the call. The vehicle now on internal power. The first umbilical tower separating from the booster. And there's the second umbilical separating. The engine starting to ramp up. The engine's firing, now building up to flight speed, and liftoff. Jack Fisher and Fyodor Yurchikhin on their way to the International Space Station. Vehicles cleared the tower, getting good first stage performance. That Soyuz delivering about 930,000 pounds of thrust from those 4 strap-on engines in the core. Getting good performance calls, nominal or normal so far for the first stage, continuing to operate well. Again, a pretty clear day there in Baikonur, so getting great views of the rocket as it flies across the Kazakh sky.
The crew is feeling good.
The vehicle already moving at over 1,100 miles an hour. And continuing to get those good performance calls, you'll hear yaw, pitch, and roll, basically the orientation of the rocket. Want to hear nominal, and that's what we're hearing. Everything going well with the Soyuz so far. Crew members still doing well.
The strap-ons burnt out after about 2 minutes before being jettisoned, leaving the core stage to continue firing for another 3 minutes or so before MECO, or main engine cutoff.
We've gotten confirmation that the escape tower has been jettisoned and the first stage has been jettisoned. Again, those 4 strap-on boosters have completed their job, dropped away. The vehicle already at an altitude of about 28 statute miles. Soyuz rocket traveling at about 3,350 miles an hour. Thumbs up from Jack Fisher. Everything continuing to go great so far with this launch. The vehicle under the power now of the core stage, or the second stage, and that's going to continue to fire until about 4 minutes and 48 seconds into the flight. So another 2 minutes and change from now.
Second stage thrusters are operating nominally.
Getting confirmation the launch shroud has been jettisoned, so the Soyuz vehicle now exposed. At this point, the Soyuz already traveling over 4,700 miles per hour.
And we have the control
Launch shroud being jettisoned.
Second stage thrusters are operating.
Everything performing as expected. That core stage of the Soyuz, 56 feet in length, 13.5 in diameter, has a single engine with 4 fuel chambers and provides between 178,000 and 222,000 pounds of thrust, depending on the altitude of the vehicle. And it burns for about 3 minutes and 28 seconds. It's going to burn until the 4-minute 43-second mark, and then it'll use what's known as a hot stage technique. So the third stage will actually ignite while the second's still burning. That's why, again, the Soyuz rocket has that open lattice-like structure in between the second and third stages.
260 seconds.
Soyuz stage separation involves the hot firing of the upper stage engines before the core stage is jettisoned. The upper stage RD-0110 liquid oxygen and kerosene engine, which has a burn time of around 5 minutes, then carried the Soyuz capsule on its 6-hour fast rendezvous space station intercept trajectory.
Parameters are nominal.
Just got confirmation the second stage separated from the Soyuz rocket, the third stage firing.
We have separation of the second stage. Yes, we confirm.
And confirmation the third stage engine has ignited and now powering the Soyuz into its preliminary orbit. That core booster separates at an altitude of about 105 miles. The Soyuz now propelled by the single engine of the Soyuz's third stage, providing about 67,000 pounds of thrust, and is going to burn for the next 4 minutes and 2 seconds.
Third stage thrusters operating nominally. SR pressure is 782. The crew is feeling good. Copy.
Getting reports the crew feeling good. Everything continuing to go great again. The Soyuz's third stage now powering it. Going to continue to operate until 8 minutes and 45 seconds post liftoff. So another 2 minutes under the third stage, and then the rocket's job will be done and the spacecraft will be in its preliminary orbit.
Third stage thruster operating nominally.
Again, all the calls, everything going well so far with this morning's launch vehicle traveling in excess of 13,500 miles an hour. And again, as a reminder, once they are delivered into orbit, a series of commands that are pre-programmed will execute. And all of the antennas will deploy along with the solar arrays.
Stabilization nominal. 510 seconds. Everything is nominal.
And with the telltale jolt, the third stage has cut off and separated.
Upper stage separation left the Soyuz MS-04 capsule in a 402 by 427 kilometer high orbit. Russian mission control in Korolyov instructing the Soyuz to undertake 1 orbital maneuver during its initial orbit and then 3 more during its second orbit to line up with the space station. It's the first time the new Soyuz MS-series spacecraft have undertaken the 4-orbit 6-hour fast rendezvous flight path instead of the conventional 20-orbit 30-hour journey. The delay in initiating fast rendezvous was caused by delays in fitting the correct navigation and communications equipment to Roscosmos's new ground tracking station. The new station, located near the Vostochny Cosmodrome in Russia's Far East, had to be equipped with the right technology to speak with the new updated Soyuz capsule. Interestingly, the capsule used for the Soyuz MS-04 mission was a late swap-around after the original spacecraft failed a key thermal control system test. Russian cosmonaut Fyodor Yurchenko and American astronaut Jack Fisher docked their Soyuz capsule to the space station's Russian Poisk module for what will be a 4.5-month tour of duty on station. The Expedition 52 pair join Expedition 51 commander American Peggy Whitson and flight engineers Oleg Novitsky from Roscosmos and Thomas Pesquet from the European Space Agency. The smaller-than-usual 5-person complement, the space station normally has a crew of 6, will conduct some 250 experiments in biology, earth sciences, human research, physical sciences, and technology development. Novitsky and Pesquet are remaining on station until early June. The Expedition 52 crew of Fisher and Yurchenko are slated to remain on board the space station until September, along with Whitson, whose stay aboard the orbiting outpost was extended into Expedition 52 by an agreement recently signed between NASA and Roscosmos. The move to only fly 2 rather than the usual 3 crew members aboard the Soyuz MS-04 follows a decision by Roscosmos to limit the number of Russian crew members aboard the orbiting outpost until the launch of their new Russian science module to the space station. The new Russian Multi-Purpose Laboratory Module, or NALCA, is now expected to launch next year, some 11 years after its original 2007 scheduled launch date. When it does arrive on station, the new module will be docked to the Zvezda module's Nadir port, replacing the Pirs docking port. But Naku has been plagued with problems, having failed key acceptance tests. These included issues with the propulsion system, replacement of leaky fuel valves causing extensive contamination and resulting in a lengthy cleanup. These delays have caused the module's propulsion system to exceed its installed warranty date, and that's forced Roscosmos to build a new replacement propulsion system for the module. The spare seat aboard the Soyuz MS-04 was filled with additional cargo. During their stay on station, the Expedition 51 and 52 crew members will conduct new science experiments that arrived shortly after the Soyuz aboard orbital Cygnus cargo ship. The Cygnus had blasted off 2 days earlier on an Atlas V rocket from the Cape Canaveral Air Force Base in Florida. As we mentioned the other day, Cygnus is also carrying 38 CubeSats, including many built by university students from around the world, including Australia, as part of the European Union's QB50 program. The CubeSats are scheduled to deploy from either the spacecraft or the space station in the coming months, with the Australian ones being launched during May. Fisher and Whitson are also slated to take part in the 5th spacewalk of this year on May the 12th. The pair's main task will be to replace an avionics box on the starboard truss called the Express Logistics Carrier, a sort of storage platform. This box houses electrical and command and data routing equipment for science experiments and replacement hardware being stored outside the station. The crew are also scheduled to receive 1 new Russian Progress resupply mission, delivering several tons of food, fuel, supplies and research materials. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts or Audio Boom. This has been another quality podcast production from Bytes.com.